This project is called GRE Geo. It was sponsored by Geothermica, European community. So I will talk about service envelopes for downhole applications. So the objective is to develop GRE casing system for geothermal wells. We'll take a look at the used methodologies to generate data points for the service envelopes. Something on, collapse behavior of downhole GRE pipe, and some conclusions and recommendations for future work. There were a lot of tasks in this project. So we started with a market study to map what is wanted by the market. We did a risk assessment and a hazard study. Besides the materials qualification, objective, there was also, development of handling tools to install these systems. So the objective is to offer a corrosion-resistant alternative to 13/3/8" and smaller steel casings. Fully of GRE casing system, so composite material that is corrosion resistant. All the necessary tools and downhole equipment was also looked at and developed. And one of the main objectives is to develop a guideline as the basis for an industry standard. Corrosion of the conventional steel casing is a serious problem. A recent investigation by SODM showed that more than 50% of the current geothermal wells in the Netherlands showed wall thickness reduction of 25 to 85%. And that is mainly because the geothermal wells in the Netherlands have a high salinity level. For this project, we defined a default well condition. So what you see here on the right is the red is the GRE casing. The selection of this well was based on the discussions we had with end users and authorities in the Netherlands. We use this as a base case. As indicated, corrosion is a real threat. And the use of a full composite material is a real solution for this type of services. There are, of course, other alternatives like GRE lined tubing systems, but there you still have a steel component that is sensitive to corrosion. So with a full composite material, you don't have that problem. So this is what the system looks like. It is a hybrid system, so the pipe material is a GRE. For the connector, we selected a carbon fiber system, carbon fiber epoxy. The reason for that is we would like to keep the outer diameter as small as possible. So one of the objectives was also, if you want to install such a system, you would like to use existing tools and drilling equipment that is used for, conventional steel materials. Yeah, so the advantages are, obvious. So no corrosion. It's, a lower capex. An alternative for high salinity wells is CRAs. Corrosion-resistant alloys, but that is much more expensive. So there is a small advantage in the smooth inner surface of the system. That has to do with you have lower friction, but also scaling seems to be an advantage as we discovered in this project. And there is also no interference with electromagnetic logging tools that are used in downhole applications. So one of the main objectives was to develop a materials say qualification standard or guideline, and actually that is based on three industry standards. So that are the ISO standards indicated here. That is in place for steel downhole casings, and there is say the glass reinforced plastic pipe standard, the ISO 14692. Say also what should have been mentioned here is the API 5C5, but that is very similar to the ISO for steel downhole products. The reason was that we adopted, say, parts from both standards to make the acceptance of the product as by the industry as good as possible. Say the target application for this system are low entropy wells, so that means for temperatures up to 95 degrees C. Say there are typical differences between say standard GRE piping or pipelines and casings. So the quadrant definition for ISO 14692 that is say different compared to API 5C5. So the axial loads and external pressure loads are more severe in downhole casings compared to surface piping. The envelope verification is based on both API 5C5 for say downhole steel tubulars and the ISO say 14692 philosophy that is a little bit different, and say the external collapse pressure is much higher than say for surface pipelines. So if you look at say the differences in the quadrants, so the quadrants in ISO 14692 that is mirrored and rotated, so that is a little bit confusing. So at the figure at the upper right, you see the ISO 14692 say envelope. So the quarter one is say the hoop axial tensile load, and the quarter two is the axial compression and hoop loads. So in the API 5C5 you see at the bottom, so you have 4 quadrants. Because compression, say external pressure is also one of the design requirements. So if we look at the, so one of the main objectives was to provide a guideline as indicated. The construction of the threshold envelope was central in this effort. So we focused on say the development and construction of these envelopes. The ultimate service envelope shows loads that result in an irreversible materials damage. Then we have a threshold envelope that represents the loads the pipe can take without the initiation of damage. I will handle here 3 of the envelopes. So that is the ultimate service envelope, the installation threshold envelope at 95 C, and the operation thresholds envelope. So if you look at the definition of say the ultimate envelope, so we see that the points, let's see if I can. Okay, so this is say the ultimate envelope. From the ISO 14692, we used to work with say an internal pressure test. So that is at ambient conditions, and that delivers this point in the say this quadrant, the Q1. Say from that the 1.0 is derived, so at the same say internal pressure level. So the difference is the way in testing. So you have with an say end cap, without an end cap. The 0, 1 is the actual tensile ultimate, and the 0, -1 is the ultimate compression ultimate. So say for the external pressure, you see it's a dotted line, and that is say based on a calculated theoretical compressive strength. Say the default well was constructed in such way or selected in such way that say elastic collapse was the governing say failure mechanism. And say for this pipe, it was not possible to say to create a compressive failure. So that means that it's theoretical value calculated as indicated in this plot. So if we then look at the resistance envelope for the installation at 95. So the 2-1 is based on long-term pressure test. So that's this black point. And actually that is the LCL value that is say constructed from a say regression test. So that gives you a ratio between this point and this point. And say the idea is to construct say the black threshold line from that. And that provides, say these points which are scaled, say according to the same ratio as indicated. So the threshold for the say external pressure that's indicated here, that is based on a 100 hours collapse survival test. And say the basis for that is that we use say parallel plate testing to measure a regression gradient for this material. And say you demonstrate that where you can determine the threshold value by a 100-hour say survival test at 95 C. Say for the operation threshold, it's actually the same as for the installation envelope. The difference is, say, the survival test that is carried out at a 100-hour, say, survival test. Say then short. Say some short information on the test methodologies. So for this project, we mainly used traditional mechanical testing, as was say prescribed in, for instance, ISO 14692 and the API 5C5, and using strain gauges for measuring the strain. So we did look at non-traditional methodologies like the UEWS. And optical strain measurements. Say for the UEWS, we decided not to take that into the guideline at the moment. Say the ISO 14692 committee is currently looking at introduction of the UEWS methodology. That's a direct say measurement method where you can directly measure the threshold levels. So then you don't need to work with these scaling exercise. The optical strain measurement, that is, we found that it worked very well for a 55 of plus minus 55 winded angle composite materials. So I will show you a picture in the next slide. We changed the design during the project. So we started with plus minus 55 system, and we changed that to a 2560 angled system. And say with that say design, we couldn't find say reasonable results using the optical strain measurements. TU Clausthal, they had quite an interesting, say, test facility for downhole piping. So they did a lot of work in the past on the steel casings. And we developed some dedicated systems to do the external collapse testing. That means that we developed autoclave test methodologies, combined collapse burst testing. So that was a very nice outfit to have on board in this project. So this is a picture of the optical strain measurement. So this is, you see a vertical line drawn here. That is the line where the strain is measured. And you gradually see the development of cracks in the system.
During what test?
This is during an internal pressure test. And you see that this is a 55 plus minus 55 system. You see gradually development of cracks. So we checked. So the advantage of optical strain measurements is that you measure the strain over say quite a large area. You can do a lot of post analysis. For instance, you can say measure the strain. So the way it works is you bring on a coating on the pipe material, and you measure say strains over the whole area between spicules that are say in the painting itself. So you can do a lot of say statistics, average measurements, means, standard deviations, and it appears to be that if you use the standard deviation of say the whole map of this area where you measure the strain, that say a deviation from linearity of the standard deviation seems to coincide with the onset of say crack development. Unfortunately for the 2560 that didn't work, so this is a start and a recommendation to take a look whether we can use this methodology in the future. So a lot of work that was put in looking at the collapse behavior of the systems. So what you see here is the collapse pressure at the vertical axis and D over T, so the outer diameter over the wall thickness. What we noticed is, say during the project that there are two say mechanisms. So you have a compressive collapse failure and an elastic collapse behavior. So the red curve you see over here is the compressive collapse, and the blue or the black one, and the black points indicates the elastic collapse. So the mode of failure in the transition area. So you see there a transition area, say the crossing between the red line and the black line. That is uncertain. You don't know exactly what's happening there. So for this project and for the guideline, we decided to stick to elastic collapse. The reason for that is that, especially for the compressive collapse, we are not sure at which level, say, failure will develop. So you don't know exactly, you know what the ultimate is, but you don't know exactly at what level, say, damage start to propagate. Say for the elastic collapse, that is more forgiving. It's an elastic type of failure mode. And we also noticed that, we can show that on the next slide. So at the right, you see a plot of a displaced volume against the external pressure during an external collapse test. If you stop the test at the maximum level, say around 200 in this case, and you unload the system and you depressurize it again, we notice that you hardly see any difference in collapse pressure. And that's also an indication that, at these levels, no damage will be introduced. So this pipe, the picture of the pipe, you see that's a typical actual failure. So when you pressurize the pipe even further than indicated at the plot right, you will get a typical actual crack. The compressive collapse failure is that it's an catastrophic failure, and it is characterized by a sudden drop in collapse pressure, as you can see on the plot at the right side, and it will provide a more severe catastrophic damage to your pipe. So to understand, the failure mechanisms we observed during the test, a substantial, finite element analysis has been carried out by Dynaflow, where we looked at the morphology of the cracks, and we try to understand by support of finite element analysis what actually happened. So then, the conclusions, the main objective was to provide a guideline based on the API 5C5 and the ISO 14692. And I think we succeeded in that. So we developed dedicated collapse test rigs. So a lot of knowledge has been gained from these tests. We developed a semi-empirical analytical collapse pressure versus DOVT prediction model. We found an excellent correlation between the predicted theoretical critical collapse pressure and the experimental results. So the long-term collapse resistance are addressed by both survival and regression tests. Implemented test methodologies like UWS and the optical strain measurements are promising, at least for certain, composite designs, but this requires more investigation. And the project provided much insight into different collapse modes, so compressive versus elastic collapse, and the width of the associated transition area. So then the recommendations, we will continue, at least the project is intending to continue testing of pipeless connector. So that has not yet been, implemented. So we developed the guideline to do the testing, but that needs to be demonstrated if that is, successful in the future. So the broader use I indicated. So the UEWS test and the optical strain measurements are promising, but also needs further investigation. As indicated, so in the guideline, we give it as mandatory to limit the casing to a certain D/T ratio. So the use of tailored laminate design can improve, design factor to provide optimized products that are competitive and reliable. So that is one of the other advantages of composite materials, that you can tailor the design to your specific needs. And that ends the presentation.